Good evening, everyone, and welcome to the eighth session of the course Dynamical System and Control. Today, again, we'll see looking at the same topic, that is controllability and observability, but we'll look in a more detailed manner. Okay, so to start off with, let me recall the definition of this controllability, what we have seen in the last session. So this is basically, so suppose you have a system given by finite dimensional ODE. So as of now, you can assume this is a time dependent matrix AT. So this is n cross n matrix. This yt is in Rn, and this control operator bt, this is n cross m matrix. Okay, and then you have ut, this is a vector in Rm. Okay, and generally we expect that m should be less than equal to n. Okay, so we say that this system is controllable if for any given data. Okay, so what it basically studies, it studies that given some initial data, can I reach some other data. Okay, so if I have been given two datas in Rn, so is it possible to find a control u. Okay, so this is something that we need to find. Okay, and this y0 y1 is given in an arbitrary manner, so it can be anything from Rn. Okay, and this control is u is what you have to determine. So is it possible to find such u so that the solution of this equation, okay, with this u, does it satisfy that at t0 point, which is the initial time, it is y0, and at capital time t it is y1. So this is the question of controllability. So given any two datas, can you reach from y0 to y1 in time interval t0 to t. Okay, so in general we generally take t0 to be 0, that okay, at t equal to 0 we have this state, and at some time t we want to reach. Okay, and you must have, okay, so as I mentioned in the last session, that this t is not at all important. Okay, so in finite dimension case, when we have this matrix and all, this controllability, so here what do you think? So suppose this t0 is 0. Okay, so what is the length, or if even if with t0, the length of this interval is t minus t0. So the question is that if you start from t0, can you reach y1 in this time? Okay, so let's say this is some t tilde. So in this t tilde time, can you reach it? Okay, so if you can reach it for some time, then you can reach it at any time. Okay, so the role of time is not important here. So if you can prove that okay, I can reach from y0 to y1 in 2 seconds, okay, then you can also reach this y1 in even in 1 second. You can even reach y1 in 4 seconds. Okay, so if you get some time, you can reach at any time. What will change is this control. Okay, so if you want to reach, suppose you got from y0 to y1, you reached here in 2 seconds. Again you find, so this is from control u1, and you find another control, you reach y0 to y1 in 1 second, and the control is u2. Okay, so you can, this u2 will not be, need not be equal to u1, and in general the norm of u2, okay, which is the cost basically. Okay, so this norm of u2 would be much greater than norm of u1, because you are reaching y1 in less time, so you will have to pay more, right? So this is what it means. Generally this is what you will see. Okay, so the time is not important. If you can reach at some time, you can reach at any time. But if you go to PD system, where the system is given by partial differential equation, it depends on the system, what kind of system you are considering. Okay, so their time might play a role. Okay, so this is what we saw, that this controllability happens if this Gramian matrix is invertible. Okay, and we saw one more condition, which was of Kalman condition, right? That rank of this matrix B, AB, A n minus 1 B, this rank should be n. Okay, so this is equivalent to this one. So maybe I should have written it as another point. So this is equivalent to this one. Okay, so this is what we have seen in the last session, and this is the Kalman condition, is what gives you the detail, I mean the logic, that okay, time does not play any role, because this is some matrix. Okay, so I'm sorry. So here basically whatever I said, when this AT and BT was time independent, okay, then this Kalman matrix, this Kalman condition holds. Okay, so this is okay, that's why I did not mention it here. So this is the case if A and B are time independent. This constant matrix, in that case you have this property, okay, and even the time does not play any role, even if this AT and BT are time dependent, okay, time will not play a role. Okay, so this was about this controllability. Okay, now let us see this concept of observability, what again I mentioned in the last session, but which was not dealt in a very detailed way. So again, let me recall what observability means. So this basically means that given a system, so okay, so here we have this kind of system. So suppose you have the same system BU, and you have some observation term, okay, Z, which is some C times Y. So you can consider this Y is n cross 1 matrix, okay. Assume this C is P cross n, then this Z is in RP, okay. So here P is less than equal to n, and this kind of thing, okay. Okay, so this is called observation term. This is observation term, okay, and this is your differential equation. This is the observation term, okay. So in this case, what observability basis? So it is kind of reverse question. So here what we were asking for, so given any initial data y0, given any two datas, we wanted to find control, okay, but here you want to recover this initial data. So far you don't know what this zt, okay, so this z is a solution, is coming from a solution, right? So this zt is C times yt, and yt is some solution, okay. You don't know about the initial data and all, you just know about this zt, okay. This zt is known to you, okay, and this C, so all this A, B and C, all these matrices are known to you, okay. So in this question what we ask that, okay, Z is known to you, can you recover the initial data which is representing? So once you get this what is initial data, you can conclude that what is my yt, okay. So the main question is to determine this y0, okay. So in this question, so you know that the solution of this is given in this form, right? So here I have written in a different way. So you know that zt is equal to this thing, this plus this quantity. So you just throw it here, you will get expression of zt, right? So why I have written in this manner is just to differentiate that what is known and what is unknown to us, okay. So this z is something that you know, this ct and all these things is something that you know, okay. You want to recover this yt naught, okay. So can you recover that? That is the question, okay. And this was answered using this kind of matrix, right? So if this, so you can clearly see from here itself at least one direction, that if you multiply by this 5 star C star, so if I multiply it here 5 star C star, and the same here is 5 star and C star, and now you just integrate from T naught to T, okay. Now this quantity, suppose this is integrable, I mean sorry, this is invertible. If this quantity in orange square box is invertible, then you can clearly write yt naught as inverse of this matrix time this thing, right? So this observability is actually an equivalent to getting the fact that this Gramian matrix is invertible. So if you can prove this fact that this Gramian matrix is invertible, you can directly conclude that the observation system what is given to you is observable, okay. That's all this observability means, okay. So you have to see that, okay, you have something that you know, from there can you conclude about the system dynamics? This is what it means basically, right? So once you get to know the initial data, that means you know that whole trajectory, right? So that is the question, okay. Okay, and as a remark you can see that this invertibility Gramian matrix does not involve this B matrix, right? Here everything what you see here is just involvement of A and C. So this control operator is not that relevant to this observability problem. Okay, so this B operator is important when you study this control problem, but here when you are trying to study the observability problem, this has no importance at all. Okay. Okay. Now let us try to understand this using some examples. So you have this equation. So this is your system, control system, and this Z is your observation. Okay. The question is, can you observe? So here what this Z is, let me write what this Z is. So this is nothing but, so yt you can write it as, so yt over here is just a 2 R vector in R2, which is y1t and y2t. This is the vector what you have. So this zt is nothing but the second component, right? So this is y2t, correct? So what it's given to you, that you know zt, that means you know the how the second component of the solution is behaving. From here, can you conclude about the whole solution? So basically you know the second component. So from here, can you know about y1t? Is it possible? That is the question of observability for this particular problem, right? So if you can, from here, if you, I mean, here in the definition what you saw is, from here can you get what is y0, that is y at t0 or y at 0. That means from here if you get y10, y20, then from here you will derive what is my y1t and y2t, and y2t is anyway known to you. So the main thing is, can you get some information about y1? y2 is known to you, can you get information about y1? That is the question of observability for this particular situation. Okay. Okay, now let us try to understand, is it possible here or not? So without going into the theory, okay, so you know one condition, that using this you can get the answer, that whether it is observable or not. But let us try to look it in a different way. I mean, just using our common sense, is it possible or not? Okay, so let us try to understand how the solution of this given equation looks. Okay, so the solution, you can write it as y of t can be written as e of 3t 0 0, e of 2t, and then you have y at 0 plus 0 to t, then you have e of 3t minus s 0 0, e of 2 t minus s, and then you have this b operator which is 2 1, and then you have us, right? So this is what you have. Now let me write it a bit in an expanded way. Okay, so from here you get e raised to the power 3t y10, e raised to the power 2t y20 plus 0 to t. Here you have, so this would be 2 e raised to the power 3t minus s u of s. Here you will have e 2t minus s u of s d of s, right? Okay, now here what you do, so you know what is my y2. So if over here, if I choose my, okay, sorry, I just, yeah, this is fine. So here if I choose my u to be 0, so I just want to remove this whole particular thing. Okay, this integral part I want to remove. So fix this u to be 0, and you choose your initial data to be, so this y at 0. If I choose something like anything here, so let me write it as alpha and 0, where alpha is not 0, okay, or alpha belong to r, whatever it is. Okay, now if we fix this one, then what will be my solution? The solution would be e yt is given by e 3t alpha, and then you have 0, right? So now here the question is, you know just about y2. Okay, so here from you can conclude that this y2 component, my zt is 0, right? But from here you cannot recover the initial data, because there are many initial data which is telling you that the zt will be 0. So you cannot determine the initial data uniquely, right? So here for each initial data, so here what I mentioned, this one, for each initial data of alpha, where alpha is varying over any, over the real line. So whatever alpha you choose, the zt will be 0. That means there are many initial data which is going to 0. That means the initial data cannot be uniquely determined, right? So the conclusion would be one cannot recover the initial data y0 uniquely. Let me just do it. Cannot recover y0 uniquely, right? So this system is not observable. So the conclusion would be not observable. Okay, and you can even check this condition, what this condition is giving to you. Okay, so if you want okay, we can calculate. So let us see here what is this. So this Gramian matrix M of, let's 0 t, this would be 0 to t, and what formula you have this. So here this is eta star, and then you have c star, then c, and then you have eta dt. This is the expression that you have this of this Gramian matrix. Now you can easily calculate 0 to t. This e of ta is nothing but e3t, 0 0 e2t, and then this c is 0 1, so this c star is this e3t, 0 0 e3t, and then if you calculate, so this would be 0 e3t, and here again you will get 0 e3t, and then this would be equal to, so 0 0 0 e60, right? Then oh, this is 2t, sorry, 2t, this would be 4t. So eventually you can see that the determinant, so this is clearly this is singular, right? Because integration, like if you do, you will get, okay, no, integration if you do, what will be the integration? Let me just see. So just copy it here. So if you integrate, you will get t, here you will get, oh, you will get 0 0 0 0, here you will get e4t minus 1 upon 4. So you can clearly see that the determinant is 0, so this is a singular matrix, so not invertible, right? So from here also you can conclude. Okay, so this was about the Gramian matrix. Now let us see this example. Okay, here you have been given the information about the linear combination of yt. What kind of linear combination it is? So this is nothing but y1t, and then you have plus half, this is y2t. So this is the observation term. So you don't know what y1 and y2 are, but you know what this linear combination is. Okay, so the goal would be to recover can I recover my initial data and hence the solution uniquely? That is the question. Okay, so let us try to see here again. So here again the solution is given by this exponential of 3t 0 0, exponential of 3t, and then y0. So nothing but e3t y1 0, and then you have e3t y2 0. Okay, so we have this as the solution. Now over here you see, if I take, so what you have, so let me write what zt is. So zt is y1t, which is e3t y1 0, and z2, and this is half e3t and then you have y2 0. Correct? You have this information. If I choose my initial data y0 to be some alpha, okay, and in the second one what I choose is I'll choose 2 times alpha, so 2 times, and sorry, with minus sign, minus 2 times alpha, suppose, and the alpha is varying over r. If I choose my initial data to be y0 as this one, my initial data, then if I have this as my initial data, then what will be z? So z2 would be nothing but, you can see y10 if I put alpha, and this would be minus 2 alpha, so this 2 will cancel, and you will ultimately get this zt is identically 0. So there are many initial data which is mapping to the same observation. Correct? The same similar kind of situation what we see, what we saw just now. Okay, so from here you can see that one cannot again recover the initial data uniquely, so not observable. Okay, so these examples are just to give you insights that what is happening and what is the question basically. Okay, so this is what we mean by observation problem. You know this zt, but can you conclude about yt? That's all. Okay. Okay, so now let us try to just this see that, okay, so far we have understood two types of notion. One is controllability, the other one is observability, and we saw that they are quite different, but they are some sort of invertible kind of thing, that in one case you know you have to find u, in other case you have to find the initial data. Okay, so a priori it doesn't seem that they are related at all, right? So in other question the control operator is important, in other one the control operator does not play any role at all, right? So it seems to be that they are not related at all, but they are. Okay, and this is the relation what we have. That's if you have a system AB which is okay. So when I say, so let me write what I mean when I say AB is controllable. So basically when I will say about controllability, I mean this system. So y prime t equals a of yt plus b of ut. Okay, and when I say about observable this thing, so let me see this, by this I mean this about this system. Okay, and when I say this a star b star is observable, I mean this system. So y prime t equals a star of y, and then you have this, what do we call this, zt will be your, this would be b star of this yt. Okay, so this is the observation term. Okay, this one is observation, and this is this main differential system. Okay, so when I say it is observable, I mean about this system, and when I say it is controllable, I mean this system. Okay, so if you have that, okay, this system is controllable, then you can conclude that this system is observable. Okay, and vice versa. So these are equivalent. If you can prove observability of this system, you can get back to, you can say that this system is controllable. Okay, and if you have, okay, so here again, like, it's kind of the same thing. So if you know that AB is observable, okay, so then its adjoint is controllable. So this A star B star is just the transpose or adjoint. Okay, so that's the notation. A star is the transpose of A. Okay, so this again the same thing. I mean, it's, these two are not different statement, they are exactly the same. It's just a way of writing, that's all. Okay, so when you have some, a pair is controllable, you take just the transpose, then that pair would be observable, that's all. Okay, and if you have some pair as observable, take the adjoint, that pair would be controllable. Okay, so this is the relation what we have, and this is called the duality relation. Duality just because this kind of adjoint appears here. So if you try to calculate the adjoint of this operator, you will get something like this, that y prime t minus y prime t equal to a star y, this kind of thing. Okay, so that's how this whole condition would come up. Okay, so this is the sort of relation what we have here. Again, this, since just using this relation, that you know what this controllability means. Controllability gives you some Kalman condition that rank of some matrix is n. Using that, you can conclude about this a star b star as well, and this is what it means. So suppose you have some system, this y prime t with observation this one, then when you say this AC, okay, so this system is observable, or in other words, we even say that a comma c is observable. Okay, so just the way we mentioned about controllability, that the pair a comma b is controllable, in the same way we can say a comma c is observable. And observability would mean that the rank of this matrix, okay, this ca dot 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 c raised power a n minus 1 would be n. The rank of this matrix should be n, and this comes up just from the Kalman condition. You know that, so here you know that AC is observable, that would give you that A star C star is controllable, and now use control the Kalman condition here, you will get the rank of this C star A star C star dot 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 A star n minus 1 C star, this would be n, and from here you just get this one. Okay, so the proof is not just by the duality. Okay, so this is what we can, this is how we can argue about this theorem. Okay. Okay, so this kind of condition we'll see. uh, okay, so for an example we can talk about this control system with this observation. So we have to check whether this system is controllable and observable or not. So when I'll say controllable, I would mean this system. When I say observable, I would mean this. Okay, you can remove this as well, so you just, this thing would play a role. Okay, so let me call this matrix as A, this one as B, and this one as C. Okay, so just what we can do is simply check the Kalman condition, this rank condition. Okay, so the solution would be this A is 1 minus 1 2 minus 1 0 1 1 0 3, and the matrix B is 2 0 1, and the matrix C is 0 1 1 1 0 1. Okay, so these are the matrices that we have. Now to check the controllability is equivalent to saying that the rank of this B, here the order is n is equal to 3, so here n is 3, m is 1, right? So see, this B matrix is 3 cross 1, here it's 3 cross 3, so n is 3, right? Here, from here you can say m is equal to 1, and this is 2 cross 3, so here P is equal to 2. I mean, this is the standard notation that we have started off with. So this is the situation, and we know that the rank of this matrix should be A B A square should be equal to n, which is 3 here, right? This is what we have. So we'll have to check whether this rank condition is satisfied or not. If it is satisfied, we'll say the system is controllable, otherwise not. Okay, so let us check what this matrix is. So first let us calculate what is AB. So AB is 1 minus 1 2 3, and then you have 2 0 1. So this first, if you do 2 and 2, this would be 4, right? And then you have minus 1 and 1, so this is minus 2 plus 1, which is minus 1, and here you have 2 and 3 5, right? This is your this AB, and then you have A square B. Okay, so A square B would be, what would be A square? 1 minus 1 2. So just square it up first. So 1 minus 1 2 would be 1 1 2, and then you will have 4, right? Then you have 1 1, and you will have minus 1 1 1 2 will give you 2 minus 2 minus 1 plus 6 7. Okay, I hope I'm doing right. Just check. Then minus 1 0 1 would give you minus 1 and then 1, which is 0. This would minus 1 1 would give you 1, and then 3 minus 2 will give you 1. Here if you do, you will get 1 and 3 4. Do it here, minus 1. If you do it here, 2 and 3 3 9 11. Okay, and then you have B is 2 0 1. Okay, if you do it, what you have is 4 8 plus 7, which is 15. Okay, and then you have 0 0 1. Then you have 8 and 11, which is 19. Okay, so so this matrix B AB A square B is given by, you have 2 0 1, then you have 4 minus 1 5, then you have 15 1 19. Okay, then you can, so to check that the rank is full, you just calculate the determinant. So if you calculate the determinant, just let me write. So if you calculate, the determinant is given by, so expand it along the first column, so you'll get 2 times minus 19 minus 5, then you have plus 1, you have 4 plus 15, which is 19. Okay, so clearly this is non-zero, right? So this is 19 basically. So you have this is non-zero, so you know that the rank would be full. So this implies, so rank of this matrix B AB A square B is equal to 3, and hence the system is controllable. Okay, now to check the observability, what we know that the observability is equivalent to saying that the rank of this matrix C CA dot 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 CAN minus 1, this rank should be equal to n. This is what we know. Okay, so here we know that the n is equal to 3, so we just need to take care till CA square, and this should be equal to 3, right? Okay, so we know that the C is 0 1 1 and 1 0 1. Okay, now what is CA? C of F A, if I calculate 1 minus 1, so let me just copy it from here. Okay, now if I do the multiplication, so 0 1 1 would give you 0 here, this would give you 0, this would give you 1 and 3, which is 4. Here you will get 1 1 2 minus 1 and 3 to 5, right? Okay, so here, from here only we can conclude actually. So you see this, if I write this matrix C and CA, C and CA, what I get is, so this is 0 1 1, this is 1 0 1, and then you have 0 0 4, you can think 2 minus 1 5. Okay, just look at this block matrix. Okay, and you just calculate the determinant. You can clearly see that these two are linearly independent, and in fact this is also linearly independent. You cannot get 4 here using these two. So you can just calculate the determinant. So let us see. So let us expand along the which row we should choose. So let us expand along the second column. So you will have -1, and then you have 4 -1, right? And this is non-zero. So this determinant of this block matrix is non-zero. That means that this matrix has rank, so this has full rank, so rank is equal to 3, and hence this whole matrix CA, because the order of what is the order, so order is 4 cross 3, so the rank cannot exceed 3. Okay, the same is true for CA square, because that is, it will have 3 columns, right? So you can say that the rank of CA, in fact you can include CA square, will be equal to 3, right? And hence you can say this would give you that A comma C is observable. Okay, yeah, just the calculation part, nothing else. Okay, if this is fine, then okay, let us look. So we saw something in the controllability section as well, that if you know that the Kalman rank is not the whole complete rank which is equal to n, I mean it is not n, then suppose it is less than n, then we know that there is some decomposition, and from that decomposition we can conclude that we have some partial controllability result, right? That okay, you can just control the first two components or just the first component, you cannot control the whole n components. This kind of things we already saw for the controllability. Similar kind of thing can be studied for the observability problem. Okay, and to motivate that, let us see this example. So this example was mentioned just before. So this is like, this is y2t and the yt. So from here you can even write what yt is. So yt is nothing but the diagonal matrix, this e3t 0 0 e2t, and then you have y0. This is the matrix yt that we have, correct? And you have, so you can even expand it further. So you have e3t y10 e2t y20. Okay, then what we saw, that just using this observation we cannot the system is not observable just because with this observation, that we already saw, right? And the reason was also quite immediate, uh, right? This was done. Okay. Now, okay, so here I'm talking about the first example what we saw. Let me just recall you. Yeah, so this is exactly this system, but okay, we have put u equal to 0. That's the one. And even when we were proving that this is not observable, we substituted y u is equal to 0. Okay, so this is just exactly this system what we have, what we are seeing there. Okay, so the system is the same. So yeah, this one. So we saw that this is not observable. Okay, so the question is, what component can be observed? So clearly, I mean, here the situation is quite immediate, that okay, here you can see that zt is y2. So from here you can actually conclude about y2 0. I mean, you know what y2 is, right? So you can conclude about y2. So from here what you can conclude, the conclusion would be that this is just a line, that the second component of y can be observed. This is from here we can say, in system what we can say, that y prime equal to, so basically this component, I mean, just restrict everything to this 2. So I mean, what I can say is circle this 2 and this one, I mean, that's it. So y prime equal to 2. So this is a singleton matrix. This is y prime equal to 2y, and observation is y, I mean z is equal to y. So this looks quite absurd, I mean, in this example, that z is y, so obviously you will have the observation, right? So this is quite easy one, I mean, here, because you just have two components, you cannot you cannot observe one of the components, so you just restrict it to the second component, that's it. Okay, so this is, so this with, write completely with observation. I mean, this is something which is very immediate. I mean, this is not meaningful at all at this level because it's vacuously true, right? Is observable. But this I'm writing just to motivate what we are going to see and what we already see for the control. Okay. So this is the theorem where you have that you can decompose the main system in such a way that you will get some component that if you restrict your system to some of the parts, you can actually conclude about that part, that okay, that part would be observable. Precisely, suppose that you have this rank of this matrix is equal to L. Okay, then there will exist some matrix P which is non-singular such that PA P inverse would be this, okay, and PB would be this. Okay, and this is the observation operator here. Okay, so this is not at all important. You can, even as of now, just you can ignore this part. So the main important thing is this and this. So the observation operator is this, and the control, the system, like the matrix A is like this. So you can write your matrix A in this form. Okay, so A is similar to this matrix. So A is similar to this matrix, and this is the CP inverse. So using just transformation, you can write your system in this way. And now if you restrict your system to this component, okay, now this A11 will be, so let me mention it here. So this would be L cross L matrix. Okay, so the order, what the rank what you have achieved here, that will be L cross L, and this would be N minus L cross L, and this would be N minus L cross N minus L. I mean, the obvious ordering what you will expect. So this is L cross L, that is the most important thing. So you'll get this, and again this would be P cross L. Okay, so where P, the C was originally P cross N, this is not P, now P cross L. Then what you can say, that this A11 C1, this pair is observable. Okay, so that's all this theorem tells you. Okay, now let us try to look at, so here the question would be how to find this P and all. Okay, so now let us try to look at this example. Okay, now this example will not be observable, just to demonstrate this theorem. So we'll see. So let us try to solve this system. So here the question is basically that you have this system with this observation, okay, and then you have to study the observability. So this example will have the partial observability property, that it will not be observable, but what can you say about which components can be observed? So that is the question. It has not been precisely mentioned, but this is what exactly what I mean here. Okay, so let us write what this A is. So the matrix A is 1 1 0 0 1 0, and then you have 0 1 1. Okay, and C is 0 1 0 1 0 1. Okay, so let us first check what is the rank of the C, CA and CA square. So let us first calculate what is CA. So CA would be 0 1 0 1 0 1 1 1 0 0 1 0 0 1 1. So here you will get 0, here you will get 1, here you will get 0, and then here you will get 1, this is 2, and this is 1. Okay. So this is the matrix what you get. Now let us look at CA square. So this is 0 1 0 0 1 0 1 and just square this up. So I'll get 1 here, and then this 1 I'll get 2, and here I'll get 0. If I do this one, I'll get 0 here, this where 1, and then here 0. If I do it here, I'll get 0, and then this would be 0 is 2, and here I'll get 1. So this would be a square. Okay, now if I again do this multiplication, what I get is so 0 1, so this will be 0, right, and here we'll get 1, here we'll get 0, this would be 1, this would be 4, right, and then here you will have this 0 1, right. I hope this is correct. Okay, then let us try to see the rank. So here the matrix would be A CA square. Okay, I think here only you can conclude. So if you look at here, so let me say this is my R1 row 1, this is R2, so this is exactly R1, right. So this is just dependent, so that would not contribute to the rank. Here if you see, this is nothing but this R2 plus 2 R1. So if you multiply 2 with R1 with 2 and then you add with R2, you'll get this one. Similarly, this is nothing but R1, and this is 4 times R1 plus R2, right. This is the property of these upcoming rows, right. So in this case, the rank of this matrix, you can clearly see that these all the four this rows will be depending on the first two rows, right. So the rank would be just 2, because R1 and R2 are linearly independent. Now this is clearly less than 3. Okay, so now the our aim would be to find the part which is observable. Okay, so our goal would be to find what is the matrix P, so that this P inverse decomposes in this form. Okay, so that would be our goal. Okay, so so here you can choose this P. So now what should I write? So this is the decomposition for observability. Okay, so now we'll decompose. So here what you can do, so the C what you have obtained, okay, you can just use this one to calculate the P. Okay, so what I will do, just I'll write the first two rows. So let P be the first two column of this matrix C, because they are linearly independent. So I can just put it here. So 0 1 0, okay, and then I'll have 1 0 1, just the first two rows of C. And for the third one, I'll just put this 0 0 1, okay, just to make this matrix linearly, I mean all these three rows to be linearly independent. Now this is a 3 cross 3 matrix, and this is a non-singular matrix, right. So the inverse exists, right. Okay, now once I choose, now let us try to calculate the P inverse. So for the determinant, you can clearly see, so I'll expand from row 1, so I'll get minus. So just determinant, let us see what the determinant is. So determinant would be this is minus 1, and then it would be 1, so it was minus 1, right. So P inverse would be nothing but 1 by determinant. Okay, so that would be minus 1, and then now you do what you usually do. So here it will be 0, here it would be 1, sorry, it would be minus 1, and then here it would be 0. Now at this point, if I do deleting this, so it will be 1 with minus sign, right? Correct. And then if I do it here, okay, now if I do it at this point, the second entry, I'll get 0. If I do it here, I'll get 0, right? So, and then here, now coming to the third one, I'll get 1. The second would be this would be 0, and here again you'll get -1, right? So this is the inverse. I hope this is correct. 1 0 1 0 0 -1 0 1. So let us check if this is true or not. So let us, if I do p inverse, am I getting identity? So this would be 1 clearly, this would be 0, this would be 0. Something is wrong, I guess. 1 0 1, if I do it here, I'll get 0, -1. Okay, something is wrong. Let me see. First seems to be correct. So -1. Okay, let me see the other one. So this, if I do it here, I'll get 1, which is correct. If I do it here, I'll get again 1. P inverse. No, something is wrong. Just, oh sorry, I'll have to take transpose. Okay, so just take the transpose here. Now I'll get, so I have to take transpose. So this would be 0 1 0, and then you'll have 1 0 0 -1 0 1. Yeah. So now let us check p inverse. If I do 0 1, this would give me 1, this would give me 0 0 0 1 0 0 0 1. Correct. So this would be my inverse. Okay. So this inverse, now I'll have to calculate this p inverse, right, to get this one. See, if I calculate p inverse, what I get is 0 1 0 1 0 1 0 0 1. Then what was your a 1 1 0 0 1 0 0 1 1, and here you have 0 1 -1 1 0 0 0 0 1. This is 0 1 0 1 0 1 0 0 1. Okay, if I do this multiplication to see what comes up, so I 0, this would be 1. Oh. Then if I do here, I'll get 1. If I do it here, I'll get -1. 0 1 would give me 1. 0 1, this would give me 0 0 1 0 1. So this would be the matrix. Now let us multiply these two. So I'll get this one as, this would be 1 0 0 2 1 0 1 0 1, right? Okay, so you can see here, so what we are expecting is of this form. So can I get this form or not, right? So you can clearly see, so here you remember this A11 was L cross L, right, the rank of this matrix. Here the value of L is, this is my L 2. Now if you see here, this is your A11, right? This is your another block, this is your third block, this is the fourth block, right? Now you can clearly see this A11 is of 2 cross 2. Okay, the order of that matrix is 2 cross 2. Okay, now what we needed to calculate another thing to find this C is to just calculate the CP inverse. Okay, that would be my another C tilde. So here you can say that this is my A tilde. Okay, and let it be, we don't even need that. So let me just calculate what is my this P inverse of C, sorry, CP inverse. So CP inverse is nothing but this matrix C, where is it, 0 1 0 and then 1 0 1, and you just multiply with P inverse, which is this matrix. Okay, now if you multiply it here, what you get is this would give you 1, this would give you 0, 0. Here if you do, you'll get 1, this would give me 0, this would give me 1, and then this would give me 0. So this is my C1, right? So this is 2 cross 2, what we expect, because L is 2 and P was anyway 2. So the C was 2 cross 3 matrix. Here we have got 2 cross 2 matrix. Okay. Okay, so this is what we expected. Now from here what we can conclude that, okay, this, the main system was not observable, but this pair A11, so let me write, A11 was this 1021 and this C1 is identity, right? So this is, you can clearly see. Okay, so this, if I calculate this rank of this matrix C11 and A11, sorry, C1 and A11, so C1 is just identity, so this has rank 2. Okay, so this is 1 0 0 1. Now if I multiply identity with this A11, so here it would be, sorry, C1 A11. If I multiply this with identity, I'll get the same thing. So it is 1 0 2 1, right? So you can clearly see that these two are Li, and this is also no, just a second. No. Okay, fine. So I don't even need these two. So this C1 is itself identity matrix. So I know that the rank of this matrix, is 2. So the rank of this matrix is obviously will be 2. I mean, obviously it will be 2, right? So this is 2, rank of this. So I don't even need to write this up, because the maximum matrix, so this is a 4 cross 2 matrix. So the maximum rank would be 2, and we know that the a block matrix of this has a rank 2. So this whole matrix will be of rank 2. Okay. So this proves that the pair A11 comma C1 is observable. Okay, so the whole system was not observable, but we have got some decomposition from where we can conclude that some of the components is observable. I mean, using some decomposition. Okay, so now this system is observable. Okay, now let me just state few theorems. So this is from linear algebra what we have. So suppose you have a row vector, this P matrix. Okay, now this is a function of time. This M is integration of Pt and P star. Okay, so this is my n cross 1. Now this is n cross n matrix. Okay, and if you integrate this again, M is n cross n matrix. So this P, if the rows of Pi's, so this P1, P2, this rows as a function, if they are linearly independent, then this constant matrix will have rank n, and the converse is also true. So the rank of n, if M has full rank, then all the functions, this Pi's, are linearly independent. Okay, the same is true for this. I mean, the similar kind of true thing is true for the Laplace transform. Suppose you have this this row matrix, this row vector. So this this functions P1, P2, Pn are linearly independent for t greater than 0 if and only if the rows of this p bar s is the Laplace transform of pt if they are linearly independent. So the linearly independentness of this vector, or these functions p1 p2 pn are is equivalent to telling that this rows of this Laplace transform of this p vector is linearly independent. So they are if and only if conditions. Okay, now these conditions can be used, okay, to get something for the control system. So you see this p star is something similar to what we have seen for the Gramian matrix, right? If you see the controllability, Gramian, or observability, we have this kind of form. The Gramian matrix has this form. So using this you can conclude this theorem. So this you have already seen that controllability is equivalent to this rank condition. What you can further conclude that the rows of this matrix are linearly independent, and this is coming from here. Okay, so this p is nothing but this is my p. Okay, so if you see here, this p star would give me the Gramian matrix. Okay, so the Gramian matrix has something like eta star b star b eta, like this kind of thing. So this is my p, this is p star, right? Similar to this. Okay, I think it was ta, the star would be here, this kind of thing. In observability the star comes here. Okay, so the invertibility of this will give you that the rows of this matrix are linearly independent. Okay, and this is further equivalent to the condition that the rows of Si minus A inverse B are linearly independent. Okay, so because the Laplace transform, if you take of this, you will get this. So the same thing what has been said here, that if you take the Laplace transform of P, with P is this one in this case, you will get this condition. Okay, so all these four things are equivalent, and let us verify for this particular example. Okay, so here this A is given to be, this is a simpler example. So what we have seen in the very first session, the last session, which was 0 1 minus 1 0. Okay, A was this and this B was 0 1. So we had this coupled system and the control was just acting on the second component, right? This kind of system we had. Okay, so here the Kalman rank condition. So let us verify this second part. So this B is the Kalman condition. So B and AB, if I see, so B would be 0 1 and AB if I calculate, so it will be 0 1 1 and 0. So this has rank 2. So you know that the system is controllable. C is what telling you ETA, B will be linearly independent. So what is my ETA? Right, so this is just cos t, sin t. This we have already seen that how to compute exponential. So this is kind of alpha beta minus beta alpha, this kind of form it has, and this exponential is given by exponential alpha t cos sin beta, like this kind of thing, right? So the exponential of this is given by e alpha t cos beta t sin beta t minus sin beta t cos beta t, right? So here alpha is 0, so we have this form. Okay, and if I multiply this eta times b, if I do, what I get is this sin t and then cos t. Okay, so you can clearly see that the rows, so here you know that already that this sin t and cos t functions are linearly independent, RLI, right? Okay, the last condition was that rows of Si minus A inverse B are LI. So let us calculate Si minus A inverse. So Si minus A inverse would be S, then you have minus A would be minus 1 1 S. So you have to calculate this inverse first. So the inverse would be, let us calculate the determinant. So it is S square plus 1, right? So it is always non-zero, and then you have S, you have 1, you have minus 1, right? This is the inverse. So Si minus A inverse times B, if I do, what I get is, so 1 by S square plus 1 You have S1, let us directly multiply. So what is B? B is 0 1, so 0 1 would give you nothing but this second column, right? So this is 1 comma S. So this is, so this is nothing but, so you know that this 1 comma S is linearly independent, and so is the, I mean, if you divide it by 1 by S square plus 1 also. So okay, to be complete, let me write this 1 by S square plus 1, then S times S square plus 1 is linearly independent. Okay, so you have all these conditions what I just stated as a theorem, so is verified for this example. Okay, so now let us go further. So now let us come to the notion of equivalent control system. So suppose you have this control system, okay, and then if you do this kind of change of variable, that is if you define your new variable y tilde as some matrix p times y where p is non-singular, okay, so this kind of transformation with, and control can be transformed in this way where S is again non-singular matrix and this is m cross m, this is n cross n, okay. Then this y tilde u tilde will satisfy this kind of system, okay, the same what we see for a and y and a and u. So you'll have this kind of equivalent system, I mean this kind of system can be written where a tilde is nothing but pa p inverse and b tilde is pb s inverse. Okay, so I mean here you can see this thing, maybe let me write it here. So this b tilde u tilde is nothing but pb, the b tilde is s inverse and u tilde is s times u. This is nothing but p b and then you have u, right? So you can, maybe if you want you can denote it by b bar. Okay, so this b bar times u, that also you can write. Okay, so it's just a way of writing in this form. So when we have this kind of relation, then we say, so this kind of relation is called equivalent. So where a and a tilde is similar, so you see this relation tells you that the matrix a and a tilde are similar, and b has this kind of property which is p b p s inverse b tilde. Okay, so if you have been given these two systems, so system 1, maybe this one, this is system 1 and this is system 2, okay, then system 1 and system 2 will be called equivalent if such things happen that a tilde and b tilde has this kind of relation. Okay, then we say that these two control systems are equivalent. This a and a tilde b tilde are equivalent if there exists matrix p and s such that a tilde is pa p inverse and b tilde is pb s inverse. Okay, and what is the property of this equivalent system? That if AB is controllable, then A tilde B tilde is controllable, and if A tilde B tilde is controllable, the AB is controllable. I mean, the controllability property is equivalent in both of the cases. Okay. In particular, you can look at this thing. Suppose you have this control system with A and B. Okay, A is the matrix corresponding to the state, and B is the control operator. Then this AB, if you reduce this A to its Jordan canonical form, right, which is much simpler, it looks much simpler using the eigenvalues, eigenvectors. If you can write A in Jordan canonical form, and I mean when you will write, you will get some matrix P, right, when you will write this, when you will try to find this J. Now using this P inverse, you can define your operator D. Okay, now studying this AB controllability is equivalent to studying the controllability of this JD. Okay, so this is nothing but the, I mean, a particular case of this. Okay, so this AB controllability is equivalent to, so you reduce it to, you reduce A to the Jordan canonical form, and B, instead of B you define D operator, which is given by the D, the matrix D, which is given by P inverse B. Then controllability of AB is equivalent to controllability of JD. Okay. Okay, so now let us come back. Okay, before, so let us see one example related to this Jordan canonical form. So in this problem, what we'll try to do is basically we'll try to calculate the Jordan canonical form of A. Okay, so our goal would be to determine, let me write here, the question is to find J, okay, and D, what I have mentioned just now. So find J and D, and then C, check controllability for this pair JD. Okay, so that is the question. So it would be a bit cumbersome. Okay, so let me, I'll just maybe let us see. So A223 133 -1 -2 -2. Okay, so this is the matrix A. Okay, so from here I'll have to find J. So our first goal would be to find this J. Finding J is easy. You just have to use the eigenvalues. You can write it in using the algebraic multiplicity and geometric multiplicity. But the main task would be to find this P and P inverse, which is more computative, right? So you have to find this P through which you get this matrix J. Okay, so let us first, try to understand what is J. So for that, let us calculate this eigenvalue. So A minus lambda, if I do, this would be 2 minus lambda, 2, 3, 1, 3 minus lambda, 3 minus 1 minus 2 minus 2 minus lambda, right? Now this would be 2 minus lambda, then you will have lambda minus 3, lambda plus 2 minus 7 plus 6, then you will have minus 2. This would be this, if you do, you will have minus 2 minus lambda minus 3, and then you have plus 3, then minus 2 plus 3 minus lambda. So you'll get 2 minus lambda, here you will get lambda square, minus 3 plus 2 will be minus 1, then minus 6, and plus 6 will cancel, then you will get this, and then you will have minus 2. So let us say this is minus 2, then you will have lambda 1 minus lambda, correct, 1 minus lambda. So let me, okay, and then you will have plus 3. From here again you will have 1 minus lambda. Yeah, I hope this is correct. Okay, I don't know, it would be too cumbersome, but just try to understand. So here we can take 1 minus lambda can be taken common, so I can write this lambda square minus lambda, I can write it as lambda square minus lambda, I can write lambda minus 1, right? So I'll write this as lambda minus 1. So I can take this 1 minus lambda common, so I'll have 3 minus, okay, so this is anyway easy, so this is 1, so this is 1, and then here from here I'll get plus, sorry, from here I'll get minus, okay, plus lambda minus 2, right? Okay, this can be written as 1 minus lambda, and then here I'll have lambda square, and then minus 2 lambda, and then plus 1. So here I can write this is 1 minus lambda, right, and this would be lambda minus 1 whole square, or 1 minus lambda whole square. So you'll get 1 minus, sorry, so you'll get 1 minus lambda whole cube. I hope I have done everything correct. Okay, so we got this thing, that 1 minus lambda whole cube. So you have the eigenvalue is just 1 with algebraic multiplicity 3, right? So lambda is equal to 1 is an eigenvalue of A with algebraic multiplicity equal to 3, correct? So now our goal would be to understand what is the geometric multiplicity. Okay, so now let us try to understand what is A minus 3i. Sorry, the eigenvalue is 1, so A minus I. So A minus I is, so this is the matrix A, so you just subtract 1 from the diagonal elements. Let me just copy it from here. So you just subtract 1 from here, the diagonal elements. So this would be 1, this would be, no, why this pencil is not working. Just a second. So this would be 2, and here you will get minus 3. So this is my A minus I, V1, V2, V3. Okay, I mean just calculate the rank of this. I hope it should be easier. So from here what you get is this rank of this matrix is equal to 1, right? Okay, so the geometric multiplicity GM for lambda equal to 1 is 1, right? So the geometric multiplicity is 1. So what will the Jordan canonical form? So Jordan canonical form would be 1 1 1 0 0 0, then 1 1 0, right? This kind of matrix it should be, or no, I think 1 will be here as well. 1 1, this Jordan would be like this. Will this be? So I just forgot what this. So Jordan canonical is basically eigenvalues, and then you have 1 on the upside. I think this should be the case. Just a second. Yeah. If I do it, minus lambda, if I do get the rank to be, would be 1 comma 1. Yeah, I think this is the Jordan canonical form for this case, right? Okay, maybe I am having a bit doubt here, so you just check. I'll check and then maybe I'll correct if this is not right. I feel this should be right, but anyway. So now you have this Jordan canonical form of this matrix A, okay, and then from here what your goal would be? Now your goal would be to, for each of the eigenvalues, okay, so find eigenvectors. So now here the geometric multiplicity is 1, so you'll get just one eigenvector. Okay, so let me write in a statement because I don't want to go into the calculation. So let me write it here. So since geometric multiplicity of lambda equal to 1, or of 1, of lambda is 1, so only one eigenvector exists, right? And you can even calculate it exist. So from here only you can calculate the eigenvector, right? So from here you can even guess, so what would the eigenvector? So from here you see that you have, from here you have the relation that v1 plus 2v2 plus 3v3 should be 0. This is what this condition tells you. So what you do, you choose v3 to be 1, right? So v3, if I choose 1, uh, just a second, so v3 if I choose 1, v2 also you choose 1, so you'll get 5, you choose v1 as minus 5. So this would be the eigenvector. So minus 5, 1 comma 1, right? So this is one of the eigenvector, right? Now to get the matrix P, so what you will have to do, so this is the first thing, the first step, okay? Then what to do, you find generalized eigenfunction. Generalized eigenfunctions, sorry, eigenvectors corresponding to the eigenvalue lambda equal to 1. Okay, now the moment you find this eigenvectors, using this, so from here you will get two generalized eigenvectors. Now you can define P. So suppose this is my V1, or let me say this is my W1, okay, and from here you will get W2 and W3, okay. You define this P as W1, W2, W3, okay, and then you can see that this P inverse AP, when you will calculate, you will get this J, the Jordan canonical form, okay. So once you do this computation for P, you can clearly check that this P inverse AP would give you J, okay. And then where is it, and then you will have to calculate this, what is my D, right? So you saw that here P inverse B will give me D, right? So then using that P, you calculate D to be P inverse B, and then so this J is anyway, it's known to you. The only why we are calculating this, so once you know the Jordan form, this P is just important to calculate this D, okay. Now once you know what is my D, you can say that you can talk about controllability of this pair Z comma P. So check, after this you just check the controllability for the pair J comma D, okay. So this is the step, that first you get the Jordan form, okay, then you just calculate. So Jordan form, either you just guess it at initial level, or you can follow this process, just follow this process to get the matrix P, and then just compute this P inverse AP, you will get the Jordan form, okay. Here I have written it directly, but you can follow this process, okay, what I have just mentioned, to get the expression for J, and then using the P inverse, which is intermediary step, here you just get this P, so using the inverse of that you can get this, the expression for D, and then check Kalman condition for this pair ZD. If the Kalman condition is satisfied, then we'll say that this JD pair is controllable, otherwise not, and then you can conclude that the pair A comma B is also controllable, or if it's not controllable, then AB is also not controllable, okay. So it's just a way of checking that for this matrix A, you can just check directly also that what is B, AB, but this is another process. So I feel that this process will make the task easier for you. For this particular example, you can see that this J A is quite complicated, right? So it has some 2-3 values, which if you calculate, it would be a bit cumbersome. But if you reduce to the Jordan form, it would be a simpler, the matrix A would become simpler, and then you can verify this. Okay, so that's another way of doing it. Okay, now let us try come back to this control problem, but now we'll restrict the control operator to be a row vector. Yes, sorry, column vector. Okay, so now we'll restrict my control operator to be of this form. I mean, okay, not of this form, I should not say, I'll just say of vector. So my B would be some vector in Rm, sorry, n cross m, so Rn. Okay, so now this B is not just n cross m matrix, but now it's a vector. So the value of m is equal to 1. Okay, okay, so for this process, so first let us try to understand the controllability of this problem. Okay, so suppose you have this nth order OD. So this is nth order OD and U is the control. So this U is the control. Okay, now you can rewrite this system in the following way. So you can write it as the first order OD in this form, where A tilde is given by this, B tilde is given by this, and this, and we have already seen this kind of uh, conversion before. So just take y1 to be z, y2 would be y1 prime, y3 would be y2 prime till none, and then yn would be yn minus 1 prime, which will give you the z nth prime, because here is nothing but z prime, this is z double prime. In the same way you'll get zn, and using the equation you can write this zn as everything you throw that side, so minus a1 zn minus 1, which will be a y n minus 1 minus a2 y, what do you say, yn minus 2, and dot 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 minus a1, so this would be an, right? Just a second, I have written, no, it's correct, and at last you'll get an minus an y1, right? So now using this you can write it in this way, and then you can check that this rank, although I'll show, I have just written it here, but I'll show for another, I mean a similar kind of thing I'll show when it will come to observability. Okay, so as of now I'm just writing it, but I'll show this. I mean it's quite easy, okay, to compute this, that the rank of this A tilde, B tilde, A tilde and all these things will give you n. So this pair A tilde, B tilde is controllable. That means this system, nth order system, is controllable. In particular, you can say in a different way, that is the pair A tilde, B tilde is controllable. Okay, okay, now why I have mentioned this all, because you have the following theorem, that suppose the value of m is 1, okay, and you know that this system is controllable. Okay, so you have that this system is controllable, then you can prove that this system is equivalent to this. Okay, so any control system, any controllable system, okay, with m equal to 1 is equivalent to this system. Okay, I hope this is clear. So any controllable system, so the first thing is that it should be controllable. Okay, that is the first condition, that the system should be controllable, and we are talking specific to m equal to 1. Okay, so this system would be controllable, then this system is controllable, then you will have that this AB is equivalent to A tilde, B tilde, what we just saw, I mean here. Okay, and this kind of matrix is called companion matrix. Okay, so this AB is equivalent to this kind of system. Okay, so this is the theorem, and the second thing is that, so here like all these things, whatever these till here everything is fine, that nothing is changing, but here there are some coefficients that come into the picture, right? So when you have this pair A comma B, how to determine this an minus 1, a2, a1, that is the question, right? So you know that A and B are equivalent to of this kind of system. So see, b tilde is also fixed, a tilde is also fixed except this one. So you have to understand what is this. Okay, although for controllability you don't need this property. So this last row is not, I mean the value of this ans are not even responsible for controllability. You can see that this is controllable, so it doesn't matter what is my this coefficients, I mean this entries, but the rank of this matrix is always n. Okay, but for given system a comma b, when you say that this is equivalent to a tilde b tilde, the constants what appearing in the last row is nothing but these coefficients of the characteristic polynomial of a. Okay, so you, this a and b is given to you, you just calculate what is my a, I mean the characteristic polynomial of a, and then from that characteristic polynomial you can, I mean pick up this a, these constants, the coefficients, and then you can substitute it here. Just take the negative of all the coefficient and arrange in this kind of form. So the constant will come in the first column, and with n minus 1 will come in the last. Okay, so this is the form that we have. Okay. Okay, so now let us do what is this? Okay, so you see here we have talked about controllability, right? That okay, with m equal to 1 if you have, then you have this controllable system. A similar kind of result is true for observability, and that is expected also because of the duality theorem, right? So we have this kind of argument that what you do, I don't know whether I have mentioned that theorem or not. I think I have not mentioned it. No, I have not mentioned it. I think I missed it, but anyway, what I mean to say that this system, okay, I'll show that this system is observable and any observation system with p equal to 1, if it is observable, then that would be analog to this kind of system, okay, equivalent to this kind of system, although we have not even defined what are equivalent observability systems, so that's why I think I did not mention. But anyway, I mean that is not important also. You can play with the duality theorem to go back and forth from observability problem to duality and to controllability and controllability to observability. Okay, so as of now let us focus on this problem and then try to see whether this system is observable or not. Okay, so again we'll do the same kind of computation. So what we'll do, so let me write it here itself. So again, if you try to convert it into a system, first order system, so it would be y1 y2 till yn. So this prime would be given by, so this A matrix. So what I'll do, I'll take y1 to be z, right, y2 to be z prime, which is y1 prime. So I'll get this kind of, so y1 prime would be y2, so I'll have 0 1 0. Y2 prime would be y3, so I'll get 0 0 1 0, and so forth. So we'll get till n minus 1, I'll get this kind of thing. And at last, when I'll calculate this yn prime, so I'll get zn, which is minus a1 zn minus 1, which is y. So let me write first this way. So minus a1 zn minus 1 dot 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 minus an z, right? Now z is y1, this is minus an y1, and similarly you will get minus an minus 1 y2 dot dot dot, here you will get minus a1 and then yn minus 1, right? So here you can write minus an, sorry, here you will get yn, so a minus an minus 1 and minus an minus 2, like so on. At last you will get minus a1. Okay, the similar thing what we have seen here. Okay, so this is the detailed calculation for that. So I'll just copy this up. Okay, let me, Okay, so this is the system that we have. Now let us talk about this observation. So observation W2 is ZT, which is ZT is Y1. So WT is Y1 of T. Right? This is my observation system. Okay, and this is the observation. Okay, and in matrix form, if I want to write it, I'll get this as 1, rest will be 0, and then you will have YT. Okay, so now here the question is this system observable or not? So for that, what we need to do, we need to calculate the rank of this C, CA, and then till CAN minus 1. If this rank is n or not, that is the question, right? So let us try to look at this condition. So you see that C is just this 1 0 0 0. Let us look at what is A square. Okay, A is this one. So let me just copy this. You know this expression for A. So you just square, if you square it up, you see this will just shift by 1. You can actually check. So if you do the first row with first column, you will get 0. If you do first row with the second column, you will get 0. But when you do the first row with the second column, this 1 and this 1 will multiply to give you 1, and the rest would be again 0. Here also you will get one shifting will be done, you will get 0 till the nth n minus 1th row will become 0 0 0, will be 0, this one, and last one we don't care, whatever it is. Okay, so this is A squares. What we are seeing, that this whole thing, just like nilpotent matrix, it is shifting by 1, this kind of thing. Okay, till in the same way, if I go to a n minus 1th, okay, so see, when we take 2 power, okay, you can see with this relation, you can actually prove it by induction. So when we take the power 2, it is shifted in the third, this row is shifted in the third, this one in the third column, right? So when you take n minus 1th power, this one will be shifted in the nth column. Okay, so you'll have 0 0 0, this last will be 1, the rest would be till here, everything will be 0, and for the last one I don't care what the entries are. Okay, and why I don't care, because when I multiply with C, so you can see here itself, let me just mention here. So when you do C A square over here, so C is what C does. C basically takes the first row, that's all. So when you multiply, sorry, so when you multiply C with any matrix, it is just going to take the first row. Okay, so C A square will give me 0 0. Okay, I didn't consider C of A. Okay, so I should mention, so this is C, and C of A, if you do, it will take the first column, which is 0 1 0 dot dot dot. C A square will take the first row, which is 0 0 1 0 0, so on, and from here if you do C A n minus 1, it will give you 0 0 0 1, right? So when you just combine all these things, you will actually get a identity matrix. Okay, so you can see that this matrix C CA CAN minus 1 will be an identity matrix of the order n, and so the rank of this matrix is n, and so A comma C is observable, right? So I mean, the way I have described here, the same thing you can do at this level. So the rank of B tilde and this whole thing will become n. Okay, so what we saw, that this system is observable. Okay, so where the observation was in the first component. So okay, here also you can see, in this case the B was this matrix, now it is basically B star. So here this B is, what is B? B is just taking the one value at the last column, sorry, last row. Now when you do this B star, okay, so B star will give you 0 0 0 1. Okay, but when you take A star also, the things would be reversed. But okay, so it's not exactly A star B star, because if you do A star, this will again come as a vector as this one. But anyway, that's equivalent. I mean, this A star B star system would be equivalent to this system. Okay, so here you see this is my A, so it's not A star as if I compare with this one. Okay, so it's not the B star, but it's just you have to interchange these two basically. Okay, okay, so here what I wanted to say is basically when you talk about the control system, what you are doing, you are taking the control at the last component for controllability. So you are controlling just the last component, but just because of the kind of coupling. So you see here you have this kind of coupling. So you just control the last component, which is yn prime. So here you will get u also. So I missed here, I think. So here you have this u. Okay, so you are just acting u on this yn. Okay, but when you go to yn, sorry, it is not yn. So this is yn prime. So yn prime, if I do, I am acting u on this yn prime system, but from here I am acting my yn minus 1 system with yn. This is a kind of coupling, right? This is a coupling. So from this yn I am getting the status of yn minus 1, but I am not acting control u directly on this yn minus 1, but through yn. So it's kind of a step we are going backwards to get controllability for all the components. But in case of observability, we are just observing the first system, the first state. That means here, where is it? So here we are just observing the first component, and then from the first component we can actually observe the whole component, all the components. Okay, okay, so now let's come back to this problem. So you have this system, okay, and this is equivalent to this system. Okay, and the question is that for what values of alpha, beta and gamma this system is controllable. Okay, so you have to guarantee the controllability of AB, which is equivalent to saying getting controllability for this system. Okay, so what we did the task would be to write this system so in the first order form. So if I write y1 y2 prime, so y1 prime would be 0 1, so this will give me y2, right? So it will be 0 1 y1 y2. Okay, and then y2 prime, if I do, this will be y1, this will be y double prime. So here I am taking y1 to be y, y2 to be y1 prime, and y2 prime would be y double prime, which is y1 double prime. So y double prime will give me minus alpha y prime minus beta y, and then plus gamma u, which is minus alpha y prime is nothing but this y1 y2 y1 prime, which is y2, and minus beta y is y1 plus gamma u. So this is 0 1, here you will get minus beta, here you will get minus alpha, and then here you have 0 gamma u. Okay, so this is the system. Right, so this is my control system. Okay, so we have to say this control system is controllable or not. This is exactly the question. Okay, so we have to consider this system. So here let us say this is my A, this is my control B control of matrix. So B A B, if I calculate, I'll get here 0 gamma, and if I act A on this, what I get is this will be gamma, this will be minus alpha minus alpha gamma. This is the matrix. Now you have to say that this for controllability what you need. So AB controllable if and only if rank of BAB is equal to 2, which is equivalent is to say that the determinant of this matrix 0 gamma gamma minus alpha gamma should be non-zero, right? This is equivalent to saying that this will be minus gamma square is non-zero, and this is equivalent to saying that gamma is non-zero. So controllability of the matrix AB, okay, here I should say this is A tilde. Okay, A and B are something that is given to you, about which you don't know, but you know this, sorry, this A tilde B tilde is equivalent to that AB. So AB controllable if and only if this rank of this is that is fine. Okay, so controllability of this AB is possible if and only if this gamma is non-zero. So you don't have to put any condition on alpha and beta, that could be anything, but for gamma you need that gamma should be non-zero. Okay. Okay, now let us come to this problem. So here you have this system y prime given in this way, where A and B are in this form. What you have to do, again here you have to find the companion matrix C. Okay, now getting companion matrix is easy. You just, as I mentioned here in the theorem, here, that companion matrix is nothing but this thing is anyway fixed. You don't have to care about this one. What you have to obtain, what you have to find is basically the last row, and last row is coming from the coefficients, okay, of this polynomial, okay, the characteristic polynomial of the matrix A, right? So in this case, getting the companion matrix C is not difficult. What you have to basically do is to find the matrix P, so that this P inverse will give you this companion matrix. Okay, and the moment you find this P, again this D you can define by PB. Okay, and then that's all. That's all you have to do. But you, from when you get this C and D, you will actually conclude that this A comma B will be controllable. Anyway, you can check from Kalman condition that this A B will be controllable. Okay, so here you see this N is 2 and M is 1. Okay, and M is 1. So first we'll have to prove that this is a controllable system. The moment we prove that this is controllable, we can guarantee by the previous theorem that this system AB. Okay, so let me write it somewhere. So the first thing is to say that AB is controllable. The moment when I prove that this AB is controllable, this would tell me that okay, this AB is now equivalent to some C comma B D. Okay, so here this B is this vector, M is equal to 1. Then controllability would mean that this A comma B is equivalent to C comma D, right? So now we have to find what is my C and what is D. That's the question. Okay, so first let us see whether AB is controllable or not. So here A is given by 2442 and B is given by 21. Okay, so let us see what is this B and AB. Okay, so B is 21, and if I calculate AB, I'll get 224 and 48, and here I'll get 428 and then 210. Clearly these are linearly independent, so the rank of this matrix is equal to 2, right? And hence what we can say, so this pair A comma B is controllable. Okay, so this a comma b is controllable. Now our goal would be to determine this c. Okay, and mainly p to get this form, to get this companion matrix. Okay, so first let us try to see what is the characteristic polynomial of a. So this is nothing but a minus lambda. If I do, this is 2 minus lambda, 4, 4, 2 minus lambda. This is lambda minus 2 square, and then minus 16. This will be lambda square. Then you have minus 4 lambda, then plus 4, and this minus 12. So this would be the characteristic polynomial. And so from here you can easily say that my c would be 0, 1, and what will be this entries? This would be minus of 12, minus of minus 12, which is 12, and here it would be 4, right? So this is the companion matrix that you have, but now you have to determine this matrix P. So basically the question is to find P. So you know C, you know A, what is the P, the transformation P, the change of basis thing, to get this C. And the step what you need to follow is the following. So what you do, the first thing is to find alpha. This is a vector, I mean this is a 2 cross 1, so maybe I should write, so this is 2 cross, so alpha is 2 cross 1, sorry 1 cross 2, and this is nothing but 0 comma 1, and then you take the inverse of this matrix BAB. Okay, take inverse of BAB inverse. This is nothing but 0, 1, and the inverse of this matrix, so let me calculate here itself. So BAB inverse is nothing but, so you just calculate the determinant, so you'll get 20 minus 8, which is 12, so 1 by 12, and then you have 10 minus 8 minus 1, 2. So this is the inverse, and now this will give you so 0, 1 will basically give you the last row. So here you'll get 1 by 12 minus 1, 2, right? So this is my vector alpha, I mean the matrix 2, 1 cross 2 matrix. Okay, this is step 1 to determine alpha. Maybe I should write in step 1. So you got this alpha. Now what you do, now from here, okay, so here you, now from using this alpha you can actually determine what is my P. So P would be nothing but alpha, and do this alpha times A. So 1 by 12 can be taken common, so you'll get minus 1, 2, and alpha times, so what was A? A was this 2, 4, 4, 2. Now when you do this alpha, multiply this alpha with this matrix here, so what you get is minus 2 plus 8, which will give you 6, and then minus 4 plus 4, which will give you 0, right? So this is the matrix P. Okay, and that's it. I mean this is the step what you need to follow. Now you can check maybe, so you just check. So from here you can, for D what do you want? So you want, let us check this at least. The D I expect should be 0 comma 1. Okay, so PB, if I do P times B, so this is 1 by 12 minus 1, 2, 6, 0, and then B was 2 comma 1, 1 by 12 which will give me, so minus 2 and 2 will give me 0, this will give me 12, so which is 0 comma 1, right? Which is what we expect, right? So my companion matrix C is of this form, right? And this D is of this form, so this is my D. So now it appears in what we wanted, the general form, which is this one. So this A tilde and B tilde, so we got in this form. Okay. Okay, no, I mean this you can actually check. So you check that P inverse of AP would give you this C, the matrix C, companion matrix. Okay. Okay, now let us come back to this sorry, not come back, but let us introduce this notion which is called feedback control. Okay, so feedback basically means that the form of control will be that it will be given in terms of the state. Okay, so here what we saw that this y prime, when I say this is ay plus bu, we don't know what is the form of u. So u can be any, I mean, of any form, but not now. What we say, this u will be said to be this feedback control if this u can be given as some k times y. Okay, now you know that this y is n cross 1 vector, so this matrix, and you know this u is n cross m, right? So uh, sorry, this is not n cross m, this is m cross 1. So this you obviously you expect this is m cross n, this matrix k. Okay, so if, I mean, this is the linear feedback, that it is of the linear form. It could be non-linear as well, but for this, I mean, since we are in the linear setup, so we will be focusing on this linear feedback control. Okay, so this is what the feedback control means, that it is given using the state. Okay, so now this is the a very important theorem. This is called pole shifting theorem. So what it says, that suppose you have this system, okay, which is controllable. Okay, so here again m is equal to 1 in this case. So when you have that this system is controllable, then what you can actually do, given, so it is controllable does not mean that uh, when you say controllable, you can be of any form. We are not talking about the feedback control. Okay, so you exist, need not be feedback, but what it says, that there will exist a matrix k, okay, such that this a plus bk, okay, will have the eigenvalues what you ask. So suppose I want my eigenvalue. So what is this a plus bk represents? So let me write this. So this is y prime is ay plus bu. Now I am saying this u is of the form bk, I mean k times y. So when I say this is ay plus b, u is some k times y, sorry, capital Y. So this is a plus bk times y. Now you just forget about controllability, you just focus on this system. Y prime is equal to a plus bk times y. Okay, just concentrate on this system. So you see that we have seen in this, when we were studying stability, that this system will be said to be stable if the eigenvalues of this matrix is negative. I mean, the real part of this eigenvalues, if it's strictly less than 0, then the solution would be asymptotically stable, right? So this theorem is what's telling us that a control will exist of this form which will stabilize the system. Okay, so suppose this y prime plus ay is not stable. Okay, but and you know that this y prime equal to ay plus bu, okay, bu is controllable. Using this thing, I mean, okay, this is not you, I'm not using this, but I mean, this is the motivation, that okay, this is not a stable. That means what we want to do, we want to put some control. So suppose my this system is this one. So this system is not stable. Okay, so I want to put some control from here, so that the system, resulting system, which is, so here I want u to be some k times y, so that the resulting system is stable. So this becomes stable. Okay, and not just stable, I mean, when I say stable, okay, so I should mention this is asymptotic stable. Okay, and not just asymptotic stable. So you remember the decay rate what you get is the maximum of the eigenvalue. So suppose I have this lambda 1, lambda 2. Suppose we have two eigenvalues and we know that these two real part is negative. Then what you can say that yt is less than equal to e raised to the power minus of, so okay, not minus, I should mention, because these are already negative, so I should just say maximum of lambda 1 lambda 2 times t. So this decay, the rate at which it decays is the maximum of the eigenvalues. Okay, so what this is telling you, it is telling you you can get whatever decay you want. So you set any set of eigenvalues that okay, I want this set to be the eigenvalues of the resulting system a plus bk. Okay, then I mean the resulting, so k is not known so far, so your desire is that I want some decay rate. I mean, more in a more general form, what I ask is that I want the resulting system to be having eigenvalues, these what I'm giving. So mu1 mu1 mu2 mu(n) should be the eigenvalues of the resulting system, and for that you want to find this k. Okay, so depending on what eigenvalue you give me, I can guarantee you that this k exists. And when I can guarantee, if I know that this system is controllable. Okay, so if you have this controllability of the system, okay, then you can, this condition is basically called complete stabilizability, that you are stabilizing the system, and not just stabilizing the system, you are saying that whatever decay you want I can give you, right? Because you can give me any spectrum, I mean any eigenvalues corresponding to that eigenvalue, I'll find k, so that the resulting system will have that eigenvalues, and hence the decay is whatever I want I can achieve. Okay, is this concept clear? So you just need the controllability assumption to get stabilizability, and not stabilizability means that the system is not stable, but you put some control, okay, so that the system becomes stable. So now this u, the role of control is not to get from one point to other point, but its goal is to stabilize the system. Okay, so now this goal is to be that u should be in the feedback form. Okay, and that is guaranteed by this theorem. So this is telling you that you can achieve any decay rate you want if you have the controllability. Okay, and how to find this k, I would not be able to discuss today, but maybe we'll start the next session by this problem. Okay, so again, the way we have found this algorithm to find what is my p, in the same way you can actually say how to find this k. So using the characteristic polynomial you can find this k. Okay, and we'll see how. Okay, so that was all for today. So if you have any doubt you can ask me. Okay, if there is no doubt we can stop here. See you next week then. Okay, bye.